I'm Cosmic Kelvin. I'm Cannon Anderson.
I'm Connor Annette.
I'm Elijah Flores.
I'm Adriana Garcia.
I'm David Lee.
I'm Riley Marshall.
I'm Daniel Rose.
I'm Mark Purins.
I'm Romeo Starfire.
And this is our presentation on Oracle. Since altitude characterization and landing exploration. For the AI AA competition, there are three primary objectives. We were chosen to pick at least one. We chose to do all three primary objectives, including characterization of the atmosphere and density profile, the geographic survey, and the identification and investigation of ore on the surface. Now, for each objective, we chose how to define 75%. For the atmosphere, we assumed that within a 100-kilometer range, measurements would be similar, and thus we could characterize the whole planet using a series of measurements. For the geographic survey, we decided to first go with a rough coverage of approximately 10 by 10 meters in resolution, followed at a later date by a high-resolution 1 by 1 meter geographic survey of the planet. Lastly, for ore quantification, we would identify several hotspots after surveying the planet from orbit, which we would later investigate in full detail on surface using landers to quantify the exact amount of ore at specific landing sites.
So the concept of operations. So the Oracle mission consists of several steps, as you can see in this graphic. The first one is the launch in November 25th, 2028 from Cape Canaveral aboard a Falcon Heavy rocket that will bring us to a low Earth orbit. Once there, the upper stage will separate from the boosters and the escape burn will be performed, starting the interplanetary travel. We calculated the transfer time to be 300 days. And as you can see, the orbiter is located inside the Falcon Heavy payload bay, as shown in this picture. Now, once we get to Mars, an entry burn will be performed. And at this point, we have the upper stage separation from the payload that will enter a highly elliptical orbit with a periapsis of 150 kilometers. This is so the orbiter can use the Martian atmosphere to gradually reduce the apoapsis to 400 kilometers. Now, this whole process will be conducted over a period of 180 days. And if necessary, a plane change maneuver will be performed during the airworking process. Finally, a final burn will be performed to raise the periapsis that it was at 150 kilometers to 450 kilometers, 400 kilometers, I'm sorry. This is to obtain our final circular polar orbit that we wanted. Also, considering both the airbraking plane change and the final burn, total maximum delta V of 5.83 kilometers per second was calculated. Now, during the step 6 and step 7, we used our scientific instruments to find suitable landing spots, as you can see. And after a period of 30 days in the final parking orbit, the EDL sequence will begin. Now, the EDL sequence consists of several steps as well, as you can see in this other graphic. First, we have the atmospheric entry, the peak heating, the peak deceleration. After that, we have the parachute deployment and the heat shield detachment. Now, every landing pod has two modules. The lower module that will have the lander that we call lower, and the upper module that will have the glider that we call accu. At about 10 kilometers, they will separate. The accu will deploy its wing and will start its science mission, collecting lower atmospheric data. The lander will start its power descent and will be followed by a sky cable maneuver that will bring it to the surface, obviously followed by a flyaway maneuver. Once we're on the surface, the solar panels will deploy, revealing the enchanter drone. Now, this enchanter drone will stay inside the lander until the glider over there is done with its mission, and it crashes far away from the landing site. Now, once that's done, the enchanter drone will deploy and will scan the surface for resources.
So in order to quantify all of our objectives, this is the science instrument that we will be using. So for our orbital, or the orbital reconnaissance bus, also known as ORB, as pictured here, we have Aster, which is a camera that can characterize subsurface ore by shooting pictures at different wavelengths. And then we have HiRi, which is another camera that takes high resolution images of the Martian surface. We have engines, which measures the concentration of different major atmospheric gases. IUVS, which collects atmospheric data, density, and composition, as well as the Mars Climate Sounder instrument, which can measure temperature, humidity, and dust content. And finally, we have MARCI, which can capture images of a Martian weather map and how it varies over time. So to the left, we have an example of Aster data, and it shows the different elevations that we can capture with this one camera. In the middle, we have an example of a high-res image, and you can see how high the resolution is. And all the way to the right, we have a weather map as captured by MARCI.
On our lander, we have 3 instruments. The first is the Mars Environmental Dynamics Analyzer. This is used to collect lower atmospheric data that will help our helicopters be able to fly. This includes wind speed and direction, air temperature, atmospheric pressure, humidity, and dust concentration. The second instrument is the Lander Vision System, which is a combination of a computer and a camera. This is used to perform terrain relative navigation by comparing pictures taken by the LVS camera to pre-existing images of the Martian surface. This will allow us to adjust our landing location of our lander by up to 600 meters, as well as avoid large and medium scale hazards. We also have the inertial measurement unit, which is used so that we can have a range trigger algorithm, which helps us adjust the deployment time of our parachute and decrease our landing ellipse by up to 50%.
And then next we have the ACIO glider, which stands for Altitude Characterization and Climate Investigation Observer. This is largely based off the Ares NASA proposal, which was never launched, but was developed and flown on Earth. So also most of its science instruments are taken from the Ares, and also some of it is taken from a MAGE glider mission, which also was never flown, but was developed. And so the main purpose of the ACIO glider is to complete lower atmosphere composition at 10 kilometers and below, using mass spectrometer and neutron spectrometer and the ionizing radiation detector. But also, because it has already built in a gravity gradiometer and magnetometer, it can also detect mass distributions below the surface, so which helps with Aster data in finding deposits underneath the ground. And the magnetometer measures magnetism, which is also good for determining like metals composition underneath the Earth or Mars. And then finally, laser altimeter and inertial measuring system are used for navigation.
On our helicopter, we have just one instrument, which is LIBS. This is used to characterize the resource deposits on the Martian surface. It does this by striking the surface with high-energy laser beam pulses, which break off pieces of material from the surface and turn those into plasma, which will emit certain spectral wavelengths that we can use to characterize the material, as well as material up to a meter below the surface.
Orbital mechanics. So for our launch vehicle, we did a trade study, and we were between these 4 different rockets, and then we ultimately settled between the Falcon 9 and the Falcon Heavy because they have pretty high payload to LEOs for a very low cost. But we decided to do the Falcon Heavy primarily because of its capability to transport a 16,800 kilogram payload from Earth to Mars through the upper stage.
Trajectory selection, we plotted our possible trajectories in a chop plot. You can see here we have 2 efficient dates we can launch, the lower one being faster and the top one being slower. However, for our mission, we did not need to get there fast, so we chose this longer travel time. We went on 300 days in order to save on both of the camera was around like 7, so we were able to stick with the 6 kilometers per second. Our launch date is November 25th, and around September 21st.
So once we complete our transfer and we end up in Mars's sphere of influence, we'll perform a 0.61 kilometer per second insertion burn, and this will put our spacecraft into a highly elliptic orbit with its payload axis approximately 150 kilometers from the Martian surface. And this highly elliptical orbit is where we begin to perform our air braking maneuver. And right when we enter this orbit, we will activate our Aster module.
Okay, so this is our air braking process. Our air braking maneuver will take about 115 days. And during this process, we'll collect upper atmospheric data as well as identify potential landing sites for our EDL sequence. The final orbit after air braking is complete will have an apoapsis at 400 kilometers. During air braking, we will begin to perform a plane change maneuver, which will be described later. The delta V to circularize our orbit after complete air braking is 0.058. This is to be able to burn at apoapsis to allow our periapsis to go to 400 kilometers. From this maneuver, we'll have an orbital velocity that goes from 5 kilometers per second down to 3.1 kilometers per second. This is from the spacecraft using drag in the atmosphere to slow down. After completing our air braking maneuver, we will perform a plane change maneuver. This is how we calculated it. In our case, we decided to do the plane change maneuver after the air braking, just for calculation's sake. And this will provide the most worst case scenario. This also includes a 90-degree plane change maneuver, which will be the greatest plane change maneuver. And from this calculation, we found our max delta V to be 5.84 kilometers per second. Once we complete our plane change maneuver, we'll be in a polar circular science orbit. This science orbit will complete a full observation for 30 days. And from this observation, we will have a 75% instrumental coverage.
We identified 4 key burns. Our insertion burn, our plane change burn, our burn, and our series of small maintenance burns. During our insertion burn, we have a relatively small 0.6 kilometers per second, and you'll notice here are very large kilometers per second delta V for our plane change maneuver. As said before, this is our maximum possible. So if our insertion ends up properly at 90 degrees right on the equator, we have prepared for that worst case scenario. Now, for these series of burns, we identified burn times. So if we burn at apoapsis, it's a more efficient burn than if we burn at periapsis. So taking within 5 degrees plus or minus of our apoapsis, we determined our total burn time. Using the total burn times, we were able to factor out a couple of types of propulsion. Now, obviously, we always want low weight and high efficiency in spacecraft, but we were able to identify that because of the size of burns, we would need many relights, and we have a relatively limited burn time. If you take, for example, ion propulsion, where a single electron is sent out the back, the specific impulse is incredibly high, but the burn times must be incredibly long and do not fit the purpose of this mission. Furthermore, because of the many relights, we understood that we could not use solid rocket boosters. And lastly, with nuclear propulsion, we deemed it too unsafe and too experimental to risk the mission on. Now, with all of these listed, we figured out that liquid propulsion was our only desirable choice, and specifically, the many relights narrowed it down to the RL-10C1, an upper stage engine specifically designed for multiple relights. With a low mass of 191 kilograms, a high specific impulse for its type of propulsion at 450, and a very nice thrust-to-weight ratio of 54.5. Lastly, for our attitude control and our maintenance, we decided that converging diverging nozzles would be sufficient. We decided that rather than using hypergolic fuels like those used on the space shuttle, which instantly combine, we would use the same O2 and H2 propulsions used for our main engine. This allows us to not introduce secondary tanks and limit the complexity of our mission. Furthermore, each of these nozzles will only burn for short periods of time, approximately 3 seconds or less, meaning that the actual nozzle wall itself can be used as a heat sink and no active cooling system would be needed.
All right, moving on to structures. So the primary structure of orb is primarily made out of aluminum 1024TL in a skin stringer configuration. However, more formal structural analysis, we want to focus on critical systems. So we decided to focus our key structures onto our solar panels, propellant tanks, and the pressure tanks. So starting off with the solar panels. So by using data collected by the Large Reconnaissance Orbiter, which had its solar panels deployed when it performed its air braking maneuver, we found that it measured a drag coefficient of around 2.25, taken at an air density relative to a height of 100 kilometers. From there, we found that the drag force acting on the area of our solar panels was around 3.06 kilonewtons. And so when we evaluated this structure, we chose to do it at the maximum drag area configuration. So in this case, our solar panels are completely perpendicular to our velocity. And to simplify the calculations, we'll just break down the structure to a cantilever beam with a point load 1.05 meters from the hinge point, which is essentially the center of the solar panel. And from there, we found that there was a maximum level stress of 120 megapascals. And from there, we were able to make a stress matrix from which we then extracted the principal stresses by taking the eigenvalues of that matrix and then going on using those principal stresses to conduct a fatigue analysis.
So we are stress of the solar panels. I say it's still the minimum because it has the low level of mass compression and low stress compared to the other ones, except for magnesium. However, magnesium is capable of burning up the air braking. So I say it's still titanium, which has been tested on the MRO doing solar braking, and we are confident with solar emission.
Yeah, so from our stress analysis, we decided to choose a 661 T6 aluminum as a material for our cylinders, and from our drag force of 3.06 kilonewtons, and our 400 cycles of loading, which come from the 400 passes done through air braking, we found that our structure has a margin of safety of 0.2 using a safety factor of 1.5. This is for static loading. And then these are our cylinder dimensions for length, thickness, and outer radius. Okay, and now this is our fatigue life analysis. So we first found our endurance limit for aluminum, which is 150 megapascals. This was taken from the fatigue life graph for aluminum at 400 cycles. And the next thing is we found that our loading is non-reversible loading, which means it happens in one direction. So it goes from 120 megapascals down to 0. This gives us a mean stress of 60.16 megapascals and an amplitude stress of the same. And using this information, we use a Soderberg ratio graph. This is the Soderberg ratio graph. Our x-axis is the stress, and our y-axis is the stress amplitude. And from this, we found a margin of safety of 0.037. And to describe the graph more, x-intercept, which is this number, is the real stress divided by the safety factor, which comes out to 160. And our y-intercept is the endurance limit divided by the safety factor, which is the 100. And this blue dot is the point of stress and amplitude, which is for our vehicle. And from this, we can calculate the margin of safety, which was found there. And okay, now for the crack propagation analysis, we found that we can have an X sensor crack size of 0.04 meters. This is found using the critical stress intensity factor for aluminum, which was 34 megapascals. And using this critical stress intensity factor, we calculated the stress intensity factor for our structure. And to do this, we used a correction factor, which assumed we had a finite lift plate.
So for our propellant tanks, we used a titanium alloy since that is very commonly used in the industry, and it gives a very high compressive yield strength for a relatively low density. And we designed our propellant tanks to be very wide to decrease the amount of vertical distance that we take up in the fairing to allow for more space to be taken up by the actual orbiter. We designed with the constraint of hoop stress because it is more likely to fail in hoop than it is in axial stress. And we designed with a factor of safety of 3, and even though that is double the industry standard, the propellant tanks are subject to boil off, which is when some of the liquid propellant converts into gas, and that causes a fluctuation in pressure. So we had a relatively high factor of safety to account for that fluctuation. Additionally, the industry standard minimum thickness for propellant tanks is 1.5 millimeters, which further increased the factor of safety that we calculated. And the increase in mass due to that factor of safety would be less than if we were to try to design this with a lower yield strength material. So we deemed a factor of safety or a margin of safety of 0.6 adequate.
The final structure that we analyzed for our structural analysis was the pressurant tanks. And for this, our priority when choosing our materials was that they be able to withstand a high pressure while also maintaining a low volume and a low mass. And so for this reason, we chose the same titanium as used in our propellant tanks, which is also the industry standard for our pressurant tanks. And we chose to use 6 tanks for this so that we could symmetrically space them out throughout the craft. And if we had just chosen to use one pressurant tank, it would not have fit within our fairing. We also chose spherical tanks because they are the most efficient pressure vessel. And we use the same factor of safety as the propellant tanks because we are accounting for boil off, which gave us a margin of safety of 0.06.
So for our mission is going to have 2 types of communication, narrow and optical. Narrow communications for short range communication between all the modules, and we're using optical communications for Mars to Earth communication. And we'll use the DSOC module for optical communications. So for optical communication, we consider 4 different antennas. We needed an omnidirectional pattern in order to avoid adding complexity to our lander. So we discarded both the patch and the parabolic antennas. And then so we really only had 2 left, the monopole and the helix. And we decided to go with the helix since it has a faster data rate and it's still omnidirectional. So to power this antenna, we decided to use the electrolyte transceiver from Alta Rose. It's wonderful. And we use the diplexer to allow multiple antennas. The diplexer allows us to both send and receive data using one antenna. For optical communications, we're using the deep space optical communications DSOC module. This module uses lasers for deep space communications, and the minimum speed is around 8 megabits per second for distance. The maximum distance with the line between Earth and Mars. So this is the longest speed we can have. And we measure a high amount of data at high rise and both the astro module to measure with, we need the necessary to have something better than radio communications. And once our module tested the psych mission successfully in 2024, and they managed to stream a from deep space using the psych mission orbiter.
Right. Power systems. So after totaling the power requirement for each instrument on each module of our mission, we found a total peak power load of around 2100 watts. This condition was used for us to this peak power condition was used for us to model our entire power system off of. Okay. To meet this requirement, we'll be using both solar power and batteries. We consider RTG reactors, but we ended up not choosing them because they were deemed too costly and heavy. All right. As far as solar arrays go, we chose a triple junction cell with layers of gallium indium phosphide, gallium arsenic, and germanium. This is because they provide the highest efficiency and the smallest size, but at the cost of weight. This is very important for us because during aerobraking, our solar panels will be extended out, and we need to reduce drag, and that will in turn reduce stress and is overall better for the health of our structure. For the orb panel sizing, we had to start with finding the efficiency of the cells, and that was using this equation right here. And it was found to be around 14% with the temperature of space. This value was then used to find the total solar panel area with this equation right here, depending on the solar flux given right here. Then area was found to be 27 meters squared. For the Enchanter drone, it will be using the same solar panels as used on the NASA Ingenuity, but will be upscaled to account for the lib system as well as the upscale in our rotor. As far as the lower landers go, they will also be using the same solar panels as on Ingenuity, but will be downscaled to meet the power requirements for our landers. As far as batteries go, we'll be using lithium ion batteries for both the orbiter and landers. This is because they use we need a high battery specific energy, and as well we also need a reasonable temperature range. Battery specific energy is important, so we can minimize on space and weight. Batteries will be used during periods of little sunlight as well. And then for the Accio glider, it will also be using lithium ion batteries, but according to the Ares glider proposal, they have a specific one chosen, which is lithium sulfate batteries. And here's a trade study of all of our batteries. Okay, and here is a diagram of our power configuration for our orbiter. Here's a summary of our solar array and our batteries. We'll be using the same batteries on the ISS right here. And on the diagram, we have a PCDU right here. It is in charge of converting the raw power from the solar panels into regulated power to then be sent to the PDDU, our distributor, which will then distribute the power to all of our subsystems. For the lower lander, is on the summary right here. There will be one lithium ion battery per lander, and there's our downside solar panels. And same kind of graph. For our Enchanter drone, they will be using 6 commercial lithium ion batteries. This is the same as the Ingenuity, but they will be upscaled, of course, in power. In the diagram, we see that the solar array does not directly power all of our systems. The solar arrays will not be in use during flight. When the drone is not in flight, the solar array will power the lithium ion batteries, which then will be used during flight. And then for our glider, just the 2 batteries as mentioned before. And then there's our system. All right. For our thermal control system, we have to consider 2 different cases. One of them is in Martian orbit, the thermal loads, and then the next one will be the Martian entry thermal loads. But for the Martian orbit, we have to consider the hot case and the cold case, one of which is on the sun side, the other one is out during the eclipse. During the eclipse side, there's no solar flux in our albedo because the sun is not in direct contact with the orbiter, and so the total heat only comes from Mars IR, which is infrared radiation, and the heat generated by the electronics aboard. And the hot case is a lot higher, so we have to basically design our thermal system based on the hot case. And so from that, we chose a multi-layer insulation blanket with 8 reflective inner layers of Captain and an outer layer of Kevlar protect from micro asteroids. And then this covers roughly about 95% of the heat incoming and radiation coming into the orbiter, which then the additional heat has to be dissipated by radiators, which are sized and weighted appropriately. And then finally, because there are certain instruments aboard the orbiter that require different temperature ranges, cold plate acting as a heat sink while doing the final heat dissipation. And this is all connected by constant conductance heat pipes, which regulate the heat within the structure. And now for the Martian entry thermal loads, we have to consider the peak heating during entry, which because we first circularize the orbit to 3.1 kilometers per second, we get a lot lower peak heat rate than compared to previous missions such as Perseverance. And also our altitude peak heating is a lot higher at 43 kilometers, whereas Perseverance, I believe, was around 35 kilometers. And from this, we chose an ablative heat shield, just a low density phenolic nylon, and those numbers. And because of the peak heating rate, we can make a really thin and therefore lightweight system. And you can see how the Accio glider is for that configuration. And then imagine below that the lower lander, and then this heat shield on the bottom in a honeycomb pattern.
Cost estimation. So our final mission cost was $969.7 million. We were able to stay within budget because we focused on using pre-existing technologies to complete our science missions.
Mass estimation. So we looked at all of the total mass for each module between instrumentation, subsystems, and structures. And then for the orb specifically, we also looked at the fuel or the expendable mass. And so our total payload mass was 7,019.1 kilograms, which since it is less than half of the Falcon Heavy's payload to Mars, we assume that we can use the reusable rocket, which saves us millions of dollars.
I've got questions. Can you guys hear me?
Yes, we can.
Cool. Also, I want to say thank you for specifically requesting that I be here. I don't know if that's true or not, but I'm honored that you think so highly of me to welcome a roast. But yeah. Also, I showed up a couple minutes late because I had to get home after a thesis defense. So I missed a little bit at the beginning. So if you covered anything that I am asking a question about, just let me know, because I might be wrong on something here. First question, back when you were talking about drag force calculations, you mentioned that you used an altitude of 100 kilometers.
Mm-hmm.
Was that 100 kilometers in orbit around Mars?
Yes.
Was that a yes?
Yes.
Okay, cool. Why'd you pick 100 kilometers?
So we looked at different research where we figure out where our atmospheric calculations go from collisionless to collision full. Back to the slides. And what we found is that depending on our entry speed, that could slightly vary. So we have seen some estimates with the rovers coming in where they started to determine the atmosphere was collision full at approximately 150. But when we compare our, were you talking about for the EDL sequence or for the solar array?
This was the slide I was thinking about. So
this slide. Okay,
yeah.
Well, then I'll pass it over to our solar guys.
Yeah, so the reason why we took air density at 100 kilometers was for a worst case scenario. During air density, we're only going to be at actually 150 kilometers, but in this case, we wanted to. There's not much data on 150 kilometers, so we just took it at 100, and we assumed this was like a worst case scenario to give us like a buffer.
Okay. Cool. Yeah, it feels very low altitude to me. For something that's got solar arrays deployed, but Mars is also a weird planet.
Yeah. So the atmosphere only starts at about 150 kilometers for Mars.
Okay.
So that is why it is. Their density was found only at 100.
Do you actually expect your spacecraft with solar panels deployed to be dipping down into the atmosphere?
No, not at all.
Dipping into the atmosphere, somewhat. It depends on what you characterize as the atmosphere. So obviously, I was talking about earlier the EDL sequences, which is slightly different, but where we assume collision full. So we looked at previous missions when designing ours, and we found the Mars Reconnaissance Orbiter determined that constantly deploying, like redeploying the solar panels and folding them back up, was very costly for the structure team. So what they did is during their similar aerobraking period, they kept their solar panels deployed. So we determined that because of how fast some of our passes near the end will be during our aerobraking maneuver, we wanted to account and keep this as a critical structure. So we don't imagine that we'd be going as low as 100 kilometers. We really shouldn't be going much lower than 150. But when designing the structure, we identified this as a critical point of failure to where if even one of these solar panels broke off, it would sincerely hamper our science mission by losing all of that power production.
Cool.
To add on to that, for aerobraking, we would use the drag caused by the solar panels to slow us down, which is the reason why we had to like find the force on the solar panels.
Yeah,
Yeah.
That was probably the one piece of information that I was missing.
Oh, okay.
And why I had the question in the first place. Yeah, if you're using it for air braking, it makes a lot more sense.
Yeah.
Can you go ahead a slide? One more. Oh no.
Sean, can I interrupt before we move on from that?
Tom's here.
Sorry, guys. Yeah, Tom's here. I apologize. I was significantly later than Sean, so I missed even more of the presentation. But I would wonder about potential performance degradation of solar panels if they are hitting enough atmosphere to act as aerobraking. Are you going to degrade a surface and negatively impact the solar array power generation?
Yeah, so our solar panels have like a protective cover over them. And at least from previous missions where they did undergo air braking, like the MRO mission, they didn't see much significant damage to the solar arrays when they were under air braking.
To go on that a little more, when I looked at the Martian atmosphere and when we were designing a lot of this, is I know my process with a lot of the EDL stuff was a little more in depth with some of it, but when we get all the way down to the surface, we're still only experiencing approximately 1% of Earth's atmosphere. So when we talk about the atmospheric effects here, they are relatively minor. Like if we go and we look at our thickness here, it's less than a centimeter for our cylinder. We're talking about some very minor forces. We're just using them over a series of over 180 passes, or 400 passes, sorry, to just slightly keep slowing our craft down so that we can minimize our delta V from our craft. So these forces are relatively
could you
minor.
maybe compare that to like a solar panel on the ISS, or I mean, in terms of I'm not even sure what a good measure of amount of impact would be. But I mean, is it comparable atmospheric density at 100 kilometers to what the ISS is? I think they're at like 400 or 500 kilometers.
I don't think so, because if there's more force acting on like the ISS solar panels, that would cause it to significantly slow down. In our case, we want the spacecraft to slow down, so our forces should be more on when it's in the atmosphere than the ISS.
Okay, yeah, I'd be interested in maybe a little bit more of a quantitative comparison there, just to give a feel, because I don't know that there are a lot of solar panels that are intended to operate fairly deep within an atmosphere for any extended period of time. So I'd be interested in kind of comparables.
Again, I'd say the best comparable involved Mars Reconnaissance Orbiter, which did the exact 150 kilometer air braking maneuver, which especially going into a circular polar orbit. And in fact, I don't remember the exact numbers, but I remember that the solar panel array that they used was actually larger than ours because they had a larger power source, or they required a larger power source, and they were able to withstand the drag force during the air braking maneuver, because they only enter the atmosphere for probably an hour at a time before leaving again, and then it's a giant elliptical orbit.
All right, so I'll turn it back over to Sean.
Oh boy, it's on me again. I was doing research on atmospheric densities. All right, I guess we got to go forward again, maybe a little bit here. So just in general, also guys, like your structure stuff right here, you're showing all of these numbers and everything like that. And you had one slide where you kind of showed a free body diagram, but like, if you actually go back that one slide. So you got, so you got this right here. Cool. It's some stresses with a thing. Go forward again. I think 2 slides. There we go. So you've got all of this and everything. Show me the free body diagram for the system and how this thing's being loaded. Like you got numbers over here for what the drag force is and what the margin of safety is, but I'd like to see where this aluminum cylinder is. Show me the actual schematic with the actual loading on it. It'd be really nice to be able to see that when you're giving me this type of data. And if we go forward again on another one, when you're talking about fatigue,
Go forward.
I mean, you jumped right in.
Forward. Yes.
I jumped right in when you guys were in the middle of structure stuff. And this is the one thing where I think Tom and I both go in on this. Like, label your axes on the plot. don't have them in bullet points off to the left. Show me a free body diagram of the loading scenario. Like, you're trying to pitch a structural analysis here. Like, you've got good numbers. I'm sure you got the math right here. But like, I want to see what you were analyzing. If that makes sense.
Yes.
Yeah. So it's like, I've got numbers, but I have to remember back to the picture that you showed 7 slides ago to think about what the loading situation is. It'd be really nice to see that here as the big picture with some nice bullet points on the numbers to go along with it.
Thank you.
Yeah. And I'll stop grilling the solar people now. Tanks.
We need you.
Tanks.
The tanks.
The tanks.
The previous.
So you
Wait.
got this one.
Yes.
Cool. Why did you go with this grid pattern on the outside?
The pattern on the outside was mostly for the CAD model, just to illustrate some ribbing on the outside that we're using to connect it to the upper stage. So if we can go all the way back to one of the orb renders. Yeah, it's a little tough to see all the way down there, but the engine.
I see it. At the
It's
very
not
bottom.
tough to see, but we have our RL10C engine here. We have our fuel tanks directly above it, and then above that needs to attach directly into the structure. And if you remember back to when we were talking about the pressurant tanks, those are going to be in this middle stage here. That center ring is where we have kind of those EDL modules that are going to get extended on a boom arm. But in these sections, we have those pressurant tanks. So we have to run a couple lines to move that fuel all the way down through the engine, as well as we just kind of ran out of space for where to store this tank. Like if we can go back to the tank slide. Yeah, we see that our main tank looks a bit like a hockey puck. So we're aware that spheres are the best pressure vessels. And then also most tanks are usually taller than they are wide. Unfortunately for us, we were really cutting it tight on space because we tried to go with the 3 EDL modules. So we had to make our tank very wide rather than very tall. So rather than encompassing our body of our structure around a lot of the tank or attaching the tank in a more structured way, we almost had to just bolt it on for what we did.
I actually like these pancake tanks better than I like your spherical tanks.
Really?
Ooh, Sean.
I know.
That's a
So
bold statement.
I know it's a bold statement. I know it's a very bold statement. But you're absolutely correct. You said that spherical tanks are better for pressure vessels.
Yes.
But are they better for storage vessels?
No, that was our big concern is if we go over to our pressurant tanks, is they're very efficient for storing pressure, but they suck for space. So we don't have the graphic on us here, but there is a certain ratio where you'll usually see as the diameter starts to expand, it becomes more efficient space-wise to go with these cylindrical tanks. So these pressurant tanks are relatively small. Since we're pressurizing them to a much higher degree, the 24 bar, we can go with a smaller amount of them spaced throughout the craft. So because we already had all that space that we had to take up vertically for those descent modules, we found that we had more than enough space in the upper stage to put these crafts around, or to put these pressurant tanks around.
Cool. I guess, yeah, I know it was a bold statement, Tom.
Oh yeah. Can I push back?
Yes.
Okay. So can we flip back to the pancakes tank?
Yes.
These are 4-meter diameter tanks, right? That is a substantially large diameter.
Yes.
And I don't know what the inside structure of your cap looks like, but the outside structure looks like it's a flat plate. Is that true of the inside structure as well?
We have a slight dome on the top and bottom. It's a little hard to show with the model here, but if you imagine that's both the on the bottom, the taller tank is the H2, and the smaller tank connected on top is the O2, the liquid oxygen. So each of these tanks have a slight domed roof. They're not just completely flat, but we did realize that this was not the most efficient design in terms of storing pressure, but we just ran out of options due to spatial constraints.
So how thick is the cap of the tank?
The cap of the tank at the minimum thickness or the maximum?
Is it tapered?
Yeah, it's supposed to be a domed roof on the inside.
Okay.
So
Meaning,
wait, it's
what's
flat on the
what's
outside, but
cross-section
domed
look
on
like?
the inside?
The flat on the outside is somewhat of the SolidWorks model just to connect them. Ideally, that would be blank space, I guess theoretically, outside of the dome.
So you'd have essentially like a constant thickness, very large radius dome.
Basically, yes.
Okay, so that's very structurally inefficient.
Okay.
Yeah, I mean, the reason spheres are good at carrying pressure is because the curvature means that the stress is fairly uniform around it, right? So a flat plate is sort of the worst case. I would very much like to see an analysis of that cap, and probably you can do it if you go dig up a copy of Rourke. Rourke's formulas for stress and strain has equations for like round plates with uniform pressure on them, fixed at the edges. So I'd want to see that kind of hand calc to tell me what's the peak stress in that flat plate and what's the deflection in that flat plate. I think you'll find that it is substantially large. Even I think you said these are what, 2-bar pressure. So it on a 4-meter diameter tank, unless that cap is substantially thick, I think it's going to deflect a lot and potentially impact other things in your vehicle, especially if you're trying to maximize space and cram things in there. So definitely take a look at that. And if you don't have a copy of Rourke, if you go down to Marston Science Library, we're kind of putting together an engineering library with those kind of resources. I think it's on its way to getting set up. So if you ask Mike Griffiths, he can probably help point you in the right direction for who to talk to find it down there.
Okay. Thank you so much. We'll get on that before our final report submission.
Okay.
Yeah, also, if you don't have time to get to Marston, you never heard this from me, but you can probably find at least excerpts of Rourke's that are relevant online in PDF format.
Yes, thank you so much.
But I never said that.
Got it. He didn't. We were gonna buy them.
Yeah, I mean, and yeah, to Tom's point also, like I agree 100%. Like the tops of these tanks are definitely going to deform unless you have some sort of reinforcement to them.
Okay.
Like I missed that it was 4-meter diameter. That's big.
They're very large tanks.
For batteries, I know you're not electrical engineers.
Yes.
Neither am I. I'm just gonna go and say it would have been good in this section to see what your power draw requirements were going to be and your discharge rates and kind of some of that information, because that's going to affect the chemistry that you select. So I'm just skeptical about the chemistry selection because of not having that seen. If you have that information, great, include it. But power draw is just as important as power storage in a lot of cases.
Okay. Something on the chemistry of what we selected is this. We saw a lot of the time historically, a lot of modules have used nickel cadmium in place of lithium ion. But what we were talking about, if we want to jump back or forward, where are the ISS slide? We talked about the batteries there.
We don't.
Oh, but the batteries that we're using is recently lithium ion has had problems with cyclical like cycles. So it has a very low discharge rate that we've seen of just losing power over time. But while we were researching, we kept getting really confused why everything used nickel cadmium when we would see lower discharge rates over time and a higher energy density for the lithium ion. And then recently we found an article talking about the battery upgrade on the ISS. And how what they did is that this new battery technology is able to better handle the rapid charge and discharge cycles that the ISS goes into. I believe the ISS specifically has a orbital period of about 1.59 hours or approximately 1.6 hours, which is similar to ours of approximately 1.9. So we were able to determine that that system we would deem sufficient, but yeah, we have not gone into the discharge rates, and we'll look into that.
Yeah, but I mean discharge rates and I mean charge rate and discharge rate are also there. How many million miles closer to the sun is the ISS than Mars? How much more solar energy is getting into those batteries and into those solar panels? So like the ISS has very, I'm trying to say is the ISS has very, it's a great starting point and a great foundational understanding point, but the ISS also is not necessarily the best example. I'm willing to bet the ISS that's been in orbit for what, 30 years now, has a much longer orbital life period than yours.
Yes.
So like not only is it getting significantly more solar energy being poured into those batteries, it's also needing to last for a significantly longer length of time than your mission. And so those requirements will both tie into the batteries that get selected.
Okay, thank you.
So just a thing I've noticed, I've learned a lot about batteries in the last 2 years.
So I'm not for batteries, but when we did do our solar array sizing and selection, we did account for the solar radiance measured at the distance of Mars. So
Okay, cool.
that was taken care of in a solar panel array. So I guess the assumption there is that well, I shouldn't be up here saying assumptions, but that should be ample enough power to charge the batteries to the power requirement that our orbiter requires.
All right.
More a little on that is that what we did when figuring out our power consumption in sizing our solar array is we looked at using a lot of our science equipment at once. So we looked at a peak output that we could expect. So if we go all the way back to, I think around slide 5, when we show our first ConOps, way back.
Yeah, this is all the stuff I missed too. So
Yeah. So if you look here, I'll run through it real quick. But we launch, and then after our interplanetary travel period, we arrive at Mars. Now, during this aerobraking period, we need a highly elliptical orbit for our Aster module. The elliptical orbit that we're going to have during aerobraking, we're going to have different science equipment for the most part operating during our polar period and during our elliptical period. So our total power draw is we decided to calculate as if we are running almost everything all the time to figure out if we can generate enough power in a 1 day period. And most of our actual science equipment, like we haven't gotten to look at the discharge rate, but most of the actual power that we'd be using or that we expect to use is under what we calculated when we were sizing those solar panels.
cool.
Yes, I have a question.
Tom, do you have anything else on?
No, nothing here.
All right. Can we go to thermals then? Cool. All right. So, oh, sorry, my dog has discovered a squeak toy. So just real quick here. So great, awesome research here, figuring out, getting all the fluxes, great call, picking to go with your, maximum thermal condition for figuring out your heat load, at least for a first pass. How did you size your radiator?
We just used the equation that was given to us.
Okay. I guess trust but verify. And also dig in, like saying an appropriately sized radiator. I'd love to see the radiator math. I'd love to see how it I'd like to see more information on it. Knowing all of the heat flux side of things is great, but that's a small portion of it. I'd rather see the actual schematic of what's your control volume here for things. How much heat is actually going into? You said you got some phase change tubing in there to handle the heat dissipation. What is your refrigerant that's being used in those pipes? What's going through the phase change? How much energy is being consumed in that phase change? You know, you got the square, you got the size of the radiator there, but there's a lot more that goes into the heat transfer of the system. That I would have loved to have seen on this. You know, I know it's one of the things that actually I will take a quick knock at our aerospace program not requiring heat transfer as a course for aerospace engineers, because this comes up and you guys are at a little bit of a disadvantage. But yeah, I would have loved to have seen.
Yeah, I just remembered, for the radiator size, basically we had a bunch of different types of radiators, and then they had a certain amount of, I think it was heat it could dissipate per like square meter of radiator, and that is how we did the calculations for the radiators. We didn't have a lot of time because we only had 1 week, so we couldn't get into really the specifics of the tubing, the refrigerants, and like all the details of the thermal control system. And like as I said, you know, some of us haven't taken that heat transfer, so we're a little disadvantaged there.
To jump in real quick, we would like to definitely go in more detail like that later. We want to use this submission for the AIAA competition, and obviously we think we're most of the way there, but yeah, we felt very limited having only a week for some of these concepts. And now we did iterate on a lot of these concepts as we went throughout the project and learned more and had to change different systems. But with only a week, we did feel like we only had so much we could go into.
Talk to Dr. Trum. He loves heat transfer. You'll make him very happy if you come to him with a fun heat transfer problem like this.
All right, thank you.
We don't have that. I guess the other thing I've got is your ablative structure. Unless Tom, do you have something to jump in on there?
No, I mean, I would just add that, I mean, you guys are a team. I didn't count how many people were in the picture when they were showing the wide shot, but you guys are a team of what, maybe 10 or so? In that ballpark? Yeah. So
yeah.
To kind of follow on Sean's point, a lot of aerospace engineering is expertise. You'll find when you get into industry, there are very few people who are generalists who can do every bit of engineering that's necessary for a complex project like this. So yeah, when you can pull in expertise from outside, do it. That's good general advice.
Yeah, if we want to jump all the way back to the libs module on the Ingenuity real quick, is that yeah, we did feel underqualified for some of these, or it was hard to find solutions. So for objective 3, specifically it asked for quantification of the orbit below the surface, and we were really puzzled because geology isn't quite our field, and there's a lot of engineering and a lot of stuff that goes into that. But we did decide to bring in some outside expertise. So I met with one of our professors here at the geology department and toured a lot of the labs that we have on campus to try to just find an instrument that we could bring to Mars and something he thought that could work, and him to explain it to us. And we were looking through, he talked about libs. They have a handheld system here in the geology building that he was able to show me. And obviously we can't bring that same handheld system there, but we found a version of a lib system on the Perseverance rover on Mars now. So we reached out a couple times for some help outside of just our professor and our graduate assistant here. But we could definitely use some more help within the aerospace department going forward.
Also, that's awesome. This is cool as hell that you did that. Let's go geology.
Geology rocked.
Yeah, back up to the honeycomb real quick, and then I'm done, and I'll let Tom. Although you didn't have any 80/20 or any really bad FEA that I saw, so the easy things are already taken care of. For this honeycomb, is the honeycomb structure exposed to atmosphere during entry, or is that substructure kind of a coating that's going to take the ablation first?
Technically, the very outside layer, because you're pouring this epoxy our low density phenolic nylon, we're pouring in as a liquid into this pre-established honeycomb structure. So
Okay.
likely we're going to have some overpour on the top to where we would just encounter the epoxy before we would encounter the honeycomb.
I got that the honeycomb was your phenolic structure.
Mhm.
I must have just misheard or something. I thought that your honeycomb was your phenolic ablative structure, and I was just gonna be like, I'm just picturing this ripping chunks off, not ablating.
No, we were just we were doing research on the ablative heat shields. Is that
And the honeycomb's there to keep it from going everywhere. Cool.
the honeycomb is just to add some structural rigidity
Yep.
so that this stuff doesn't, come off in chunks.
Yep, cool. Nope, we're all good. That was my only thing. I was just like,
Mhm.
I don't know what's going on. I don't know if you could have made it. I guess the only thing you could have done to make it more clear would have been in this bottom picture where you got the honeycomb, pointing to the inside of the honeycomb structure and saying phenolic for like phenolic ablative fill or something like that.
All right, we'll do that going
Like
forward.
for your final report, just if you're gonna have this schematic in there, show what all the components of it are in the picture.
Okay.
It's just a nice way to do it. It'll make, also if you're gonna be submitting this to an AIAA competition submission, it'll be good to have really good quality figures
Mhm.
that are really explanatory of the system. But,
Okay.
but yeah, otherwise that's it. And good job, guys.
Thank you so much.
I'm sorry I missed the first like 15 minutes of it, but
Mhm.
I missed all the good stuff. Not that this wasn't good.
We have one last slide for you.
Oh no.
We're anticipating a certain question that we didn't quite get to. Keep going. We're hoping trying to do some research with some of the questions you guys asked earlier and saw that a lot of people specifically got grilled on some of the structural calculations, but you never quite asked us.
That
Your answer.
that grilling on a structural question was because of a group that designed an airplane wing and didn't know how an airplane wing was going to be loaded in flight. You guys, I don't think are in that same category, but still, I appreciate this.
All right. Well, thank you so much for coming and thank you for your questions.
Did you make a slide for Tom also?
We just have some other appendix figures. I see anyone like that.
All right.
I say that I'm tickled by this slide. I like it.
It's a good slide.
Thank you.
Any shear moment diagram is a good slide for me.
But yeah, try to add a lot more free body diagrams in our final report and work with that. Thank you, guys. Thank you. Any questions over here before we go? No?
I'll ask you guys one.
Mhm.
Can you go back to arrow breaking?
That one?
All right, awesome. Just a quick question. Why did you decide to do arrow braking and the inclination change separate?
It was just
Oh, yeah, so we just calculated separately, but because like we couldn't calculate the plane change while we're undergoing air braking because like the apoapsis is constantly changing. So we did the calculation for the plane change, assuming we finished air braking already.
Furthermore on that, this gave us with a higher delta V budget, which if we think back to our hockey puck tanks, they were slightly upscaled. So for our initial mission budget, we calculated, I believe it was 10.67 cubic meters, which we then upscaled to about 11. And then remembering again, our plane change maneuver is our worst case scenario, is that we anticipated having a lot of extra propellant, hopefully, so that we could extend our mission lifetime. For the AIAA competition requirements, our mission was to conclude by 2033, which we have, the way we defined all of our objectives, we can complete them by that 2033 deadline. But obviously with that high-rise camera, the longer they allow, or the longer we pay for ground teams to keep working on this mission, we could continue to collect really, really high-quality data from Mars. So we were hoping that we had a slightly extra delta V built into the budget so that if a further budgetary allotment to continue the mission lifetime gain forward, we would be able to keep working.
Awesome.
That was just another kind of comment would be, you can also use arrow braking for an inclination change, so that may help you as well. So,
I didn't know that.
We didn't know that.
so just if you want to like decrease that delta V even more,
Mhm.
you know, it's essentially free delta V at the end of the day. So
Yeah. That might
it's just something to, you know, maybe comment on in your final report.
Okay, thank you. That's it.
First, I want to say thank you, Tom and Sean, for your questions. We really appreciate your suggestion, and I definitely believe that they will make their report better because of your comments and suggestions. So for the presentation, I think you guys did a great job. Like even the rehearsal between 3 p.m. and 4 p.m., you guys will make great improvement. And for the presentation slides itself, I think it's very comfortable read, and the presentation style, I think it's like, well, I feel it's really great. And the Tom and Sean already covered a lot of topics and Trey. So there are just some small points that I want to mention. It's not necessarily correct, but just in case, if you guys want to consider in your let's say future presentation or final report, or the one that you will submit to the academic competition. Or if you can submit to some conference, you still need to do presentation, right? So the first one is on this slides. There's no page number.
Can we go to the Accio? The slides are slightly out of date.
So in terms of presentation, I feel like you guys did a lot of explanation of the glider and the instrument on this glider, but this graph, you guys didn't do any explanation. I mean, what's the point to put it here if you don't want to explain it? This one.
Yeah.
Yeah.
I just pulled that, sorry, I pulled that straight from the proposal. They have just different names for those instruments like CNDH, you know, command and data handling, not chef, the ultra, no, the antenna. Yeah, I suppose for future reference, we could make this item ourselves.
The thing I feel that for the presentation itself, if you don't have time to explain it, don't put it there, because it's gonna like extremely confuse. Like I see this one and I want to figure out what it means, but you guys didn't even spend time on it, so it's better not put it there, right? So this is in terms of presentation, and also for the launch vehicle, you guys, I think this is the trade study. For all the trade study in this one, you probably need to consider like, instead of only listing the things, I want to see like, let's say for the thrust. I mean, what is the goal? And then I can compare, okay, these are the several options and my goal is water level. And we can see, okay, which one is best for our application instead of only list the information here, right? Because really, thrust is not higher the better. And also like the capability of carrying the payload is not higher the better. It's like which one fit your application the best. Right. So, and also like showing the capability to transport 16,000 kilograms payload to Mars, but your estimation at the very end is 7,000. So again, I would prefer like, okay, these are all the options, all the information, and our goal is this one. That's why we choose which one. Right. So we want to make a clear logic why you make this decision instead of listing all the information. So, in your final report, you probably need to think about like, when you do the trade study, I want to see like, on top of all the information, why I choose this one.
Okay.
Yeah. And for the graph of this one, I feel like, well, I don't know much about the mechanics, but I feel like when I see this graph, wow.
Yeah.
So whenever you put something there, you make a point, and you know, like to the audience can really get information from this graph. I mean, for all the red color, I mean, yeah. So for the report you're gonna submit to for competition, you probably be like, well, if you can explain it very well, that's fine. But if you cannot explain it very clearly, it's better not put confusing things in the report, in the presentation. And for the structures, change the structures.
Go back.
Start from here. I don't know much of the like aluminum 2024 TL. So what does TL means? We don't know.
It's one of the aluminum.
T3, T4 is like but is there really a TL?
That's what I was saying. That's really in these minutes.
Check, yeah, material. No, there, go back.
No. They,
No, go to the material selection. Slide.
I think it's a no, because I was participating on other.
That is definitely something that
It's
we
not a
will fix on the final report.
Because from what I remember, it's like, okay, like T3, T4, T6, they're like raising the temperature to a certain level and then decrease to, and then the temperature is different and the speed of reaching to temperature and cool down is different. So that's we have different heat treatment procedure, and that corresponding to different T. Yeah, but I don't know what's like really TL means. Maybe something new. Try to Google it. I didn't find any information about TL. So just be careful in the report. Don't. Yeah.
that might have been a typo. Sorry.
The next slide. The next one.
Next slide.
So here you do the calculation, and this one you said, okay, when the wind is perpendicular to the panel and you have the maximum stress, you approximate. I know as engineer, as Enneagram project, we always simplify as some model, but this is obviously a distributed load. When you approximate a point load, we have the capability of solving problem with distributed force. But why you put it as a point force?
I think we might have done it as a point force when we were calculating, because we were doing a lot of our stuff with Excel sheets, is that it might have just been a more simple way for us to iterate through different designs and different sizes.
So here's the thing, for our sim design for the Enneagram class, it's like, if we don't have the capability to solve that complicated problem, it's like if we distribute those, it's like, yeah, then we can simplify in a certain way. That's okay. But I think in our I assume you guys already took mechanical materials, aerostructures. So I think from the class we have taken, we have the capability to solve a problem. If it's a chemical beam problem, if it's distributed force instead of point. We want to do the simulation as close as possible to the real situation. Like real situation is distributed force. So, and we have the capability to solve the problem with distributed force. So just use distributed force.
I guess part of it though was that the distributed force would vary. We don't know how it would vary, but because like the edge of the panel would not have as much drag force as like the center of the panel. I think that's part of the reason why we chose a point load, because we know the center of the panel would experience the most drag force compared to like the edges. And I guess that was kind of.
Sorry, can you repeat it?
So like the edges of a panel won't experience as much drag force as like the center of the panel.
Why?
Because
I got it. If we're looking at just wings in general, we know a lot of the times if we just look at commercial aircraft, they have the tips on the very end to try to deal with wingtip vortices, is that we're going to see different behavior going around versus just a blunt collision, where around that center area of the solar panel, we're just going to encounter a blunt smashing into the atmosphere, as opposed to as we get closer and closer to the wing, some of the pressure may be able to vent around the sides more efficiently. So that distributed load would not be uniform, and I don't think they felt like they were able to model that distributed load.
Well, you can figure like it's not uniform, but how much variation it has. If, again, we approximate to some simplified model, but if the variation is not really that large, we can still use if you use a uniform distributed force, it's still better than a point force.
Mhm.
Do you know what I mean?
Okay.
And also, I want to know that you put in point force and where is the 3.5, 3.05 from?
That's to the center of the.
That's from. So we found our like stress element up here, and then the center would be like here. For
Center. Why not the tip? Why not the free end? So if you design let's say, okay, I don't have capability to model this one actually force, and you want to use a point force, but using the point force applied as center is actually very dangerous. If you really want to be conservative in the design, that instruction will not fail. I think it would be better that you assume that the conservative force is at the free end. That makes sense?
I think we have that consideration of maximum moment would occur at the end, but then we also were considering.
You want to be conservative in the design.
Yeah, I don't know.
Yeah, so it's like you put a point force at the center of the panel. You must give me some justification why you do that.
We'll work on that for the final report.
Yeah. Yeah, because let's say if you really want to simplify it and to have a conservative design, well, you should probably put the force at the free end, right? And next slide. I'm glad that you guys changed the BQ and the one you sent me on canvas is the FFA. In the final report, try to be careful, don't try to fool me, because that one FFA you have 1 megapascal, and here VQ of IT you still have 1 megapascal. So I want to know if you just changed the equation and didn't do the calculation. You guys do the calculation.
We did the correct calculation. At first, it was just when we were trying to get the slides in.
Okay,
We made a mistake.
Well, for our stress element, it was like 0, but like this was for like at this point.
Okay, what is Q you used?
I don't think I
We would have to get back to you.
Excel question. Excel, don't remember.
Yeah, so in the final report, I do want to you guys like try to be detailed in this kind of calculation because it's not just somebody change FFA from the original size to VQ of IT, because let's say VQ of IT, you need to let me know what is the Q you use and how do you calculate Q and what is the location of the Q, right? And also for the I don't really think it's necessary to put like 120.3067. Again, single digit is not necessary. Yeah, and also like for the 3 eigenvalues, I would prefer you just put sigma 1 equal to 120 megapascal and sigma 2, sigma 3 equals to, because convention is sigma 1 greater than sigma 2 greater than sigma 3. And this is the static stress analysis, but the feeling, you guys may have the complete calculation in your report, but the feeling you give me this slide here is that your calculation is not done yet. You start at principal stresses, and what is the thing after that? Fatigue, you should have a static analysis, right?
Yeah.
But your static analysis start at principal stresses. You know what I mean? To prove to me that your structure is safe in static loading situation. So I want to know principal stress is something in the middle. And then they say, okay, based on the principal stress, I use, because it's aluminum, I use moment stress theory or Banksman shear stress theory. And this is the material property yield strength of whatever material you use. And there's a safety factor we want to use. And so this is safety margin we calculate based on the thickness and everything. That is a complete static stress analysis, but your stress stop at principal stress in the record.
If you go to like the next slide. Oh, it's the one after this. This is where we kind of talked about the margin of safety and the safety factor for the static analysis. But yeah, it was separated by, so if you go back, so we had
We
this
should have moved that
material
material slide.
Yeah, we could have moved this material selection slide somewhere else.
Yeah, so basically it's like, again, it's back to the logical thing. So when you try to explain something or try to put put on slides, the logic should be clear. And you should not jump here and there and put scattered information because I do want to see a clear logic. And also for next one, no, I think this one. Yeah, so you are listing the arming strength, compressive yield strength, tensile arming strength. I'm curious why use tensile arming strength instead of tensile yield strength? That is compressive.
She's asking why listed.
Why you chose for the tensile? Why you chose the arming strength instead of yield strength?
Do we know if we made if that was supposed to be compression ultimate or if
This was just the graph.
The graph of what?
The different material table that.
Yeah.
So you need to know why you showed this information, right?
Yeah.
So you chose arming for tensile. Why you chose arming strength instead of yield strength?
There was no specific
There's
reason
no
to
reason.
use. Yeah.
Yeah, we could have removed this column because we never use this for any calculations. We always use the yield strength for the calculation.
Compressive yield strength?
I believe it was.
Doing bulk analysis,
No.
but why you use compressive yield strength?
We use that for the pressure tank.
But you pressure and compressive stress. Right?
If you're looking on the inside, the pressure is like pushing out on the structure.
It's tensile. It's tensile.
I don't
I
know.
believe because these values were the same.
No. It's not same.
They're not.
no, they're
Same.
I think concrete, for example, is very, very good in compression, but for that intention.
I think it's more compressive than tensile. So when you guys show me something, you cannot just, oh, this is just table we made. I mean, I need to know a reason why you show me this information, right? And also, I mean, I'm glad you guys put density and put the element strength. It'd be nice you have like strength to weight ratio kind of thing because that's very important for for us to see why you choose specific material and for anything that can fly. And the next one can survive 400 cycle. What does it mean? Is your expectation or based on your calculation?
Expectation.
Expectation.
We need this to survive 400 cycles.
Okay.
So if we were to go all the way back to that aerobraking slide, I think it did cut off early, but we are expecting 400 cycles
Okay.
where this would be loaded. So obviously we see that our margin of safety here for our static loading scenario
Okay.
was higher than we would like. But then when we went forward and we looked at that cyclical loading analysis and the fatigue, that was our limiting design criteria. So that's where we found our lower margin of safety.
Okay, so how did you calculate it? Like, calculate the number of cycles that your structure can survive?
Oh.
What kind of fatigue analysis did you get?
Excellent.
So we used there was like a fatigue life endurance limit graph for aluminum.
Yeah, that's one thing I want to ask. Aluminum does not have endurance limit.
Well, no, not the at 400 cycles though. So like on the graph, there's like a
You cannot.
cycle endurance limit, but there's also an endurance limit for. I thought there was an endurance limit for like a certain amount.
That is not endurance limit. You cannot say like 400 cycles is endurance limit. Endurance limit is specific terminology used for 10 to 6 cycles.
Yeah.
400 cycles is in the low cycle fatigue.
Yeah.
You cannot say that stress level corresponding to 400 cycles is endurance limit. You know what I mean?
I mean, I would have to show you the graph, but I don't know. Like,
Endurance limit.
You did it wrong.
I mean,
I think we just need to look at it again. What should we look into for the final report then? How should we do this instead?
We can talk about that in detail later, yeah.
Thank you.
Yeah, if you know 1% what induced limit mean, don't try to like, yeah. There's a different cycle, there is equivalent stress level. But endurance limit is only for when it's 10 to 6. It's corresponding to SE, endurance limit. But you cannot say 400 is also endurance limit, 1000 is also endurance limit.
Oh,
10 to
and
6.
so like for steel, right? If it was steel, would you take the endurance limit? Because it would go to 0, or like not 0.
Steel does have endurance limit.
Yeah. So that would be the endurance limit when it plateaus?
Yes, for steel. But that is about around 10 to 6. You cannot say 400 corresponding to endurance limit, no.
Okay.
Yeah. And on this slides, critical stress intensity factor 34 megapascal. Do you see the problem here? For critical stress intensity factor.
It was like Pascal times the square root of not inches, meters.
Thank you. It's beta sigma squared pi a. How can you have a unit of megapascal? That's a square root of 10, right?
Yeah.
Meter. So we put some information here to like we are senior engineers. We cannot just put random information like, yeah. We are professional trained in the past several years. So be very careful when you put information here. And also, I think they already comment on that graph. Try to improve the final. Yeah. They already commented. I have great comments on this stress analysis, and also I want to say that you guys do the analysis on the sidewall, right? The like 1.5 millimeter is the thickness. Is it? Because I just see some like what is frame and stringer, and that should be, if you consider that is a stress carrying structure, like your calculation should be different, because right now I see your calculation is based on like uniform thickness without that frame and stringer. But now since you have the frame and stringer, I would expect that they should be the main stress carrying structure. And so in your calculation, you should consider that. Right.
Yeah.
So Cheng, I would say with that design, the wall, the sidewall of those tanks, right, is going to be under more or less uniform tension. Where stringers help you is where you're in compression, which you're not going to have in a pressure tank that I don't think is intended to carry like axial load, like axial compressive load in your structure, is it?
Yes.
Oh, it is?
Yeah, the calculation.
The stringers on the structure, we do expect a compressive load during launch that this would need to bear if we are able to go like all the way back to the we don't need to, but all the way back in that initial ConOps graphic, the capsule is stored upside down. So we do have all the weight of the actual fluids weighing this down, as well as the engine above it. So during launch, we do expect
so yeah, you're going to have some like compressive buckling load that is those stringers are reacting. The other thing they're going to do is they're going to stiffen the interface between the sidewall and the cap, which is going to want to bend a lot, and those stringers are going to help stiffen that as well. Yeah, I hate to say go to a FEM, but for an oddball situation like this, I think that's probably justified to see what specifically is going on there and you know how that joint is going to react, because it's going to be weird.
Okay, thank you.
Yeah, I think I think it's the same comment for the power source. It's like again, the trade study, as I commented, you guys put the information here, like and also they have great comments like you should add more information like the power draw and discharge rate, charge rate. And also one thing I want to say that you guys put all the information and you don't even have like what is your own expectation in each criteria.
Mhm.
And then you have a conclusion why I choose specific one, right? So the trade study is not just listing all the information, but I also want to hear some. Okay, so here is all the candidates, here the information of all these candidates, and here is our requirement for our design. And now because we want our decision is optimized for our design, we chose this one. So it's not just simply list information. I want to see a clear logic why you make some decision. I think we had previous groups, previous class, they made something like, I don't know if you have seen that before. It's like they put a weight on each criteria and put a score on each criteria. And in the end, they calculate, okay, the weight times score, and then which one has a high score. And that's how we chose. Right. So yeah, that is one option. You can think about it, but I mean, it does not need to be in that way. Yeah, just. That's all comments I have. Very well. I mean, for the weekly report, I talk about it with Trey. You guys did a really great job. I really appreciate that. And also for the presentation, everything it's amazing job. And thank you for the leadership. I mean, you guys. I mean, I can feel that you guys like contribute to the group work and work together, and everything is like, yeah. I really appreciate that. Great job, everyone. Yeah.
Thank you so much.
You're welcome. Do they have any questions?
Do you guys have any last questions before we go?
It's fine. Okay.
Go ahead. I think